These revelations rocked the scientific world. In one of the planet's most remote corners, geologists detected a deadly threat long believed dormant. A 1,000-kilometer fault lies in the frozen crust beneath dense northern forests, suddenly showing signs of life. Satellites recorded movement in the frozen crust where no one expected it. Scientists were stunned by the scale. The looming tremor could exceed magnitude 7.5, and within 20 kilometers live communities unaware of the danger. But that's not all. Researchers warn that destructive consequences could spread beyond Canada. Seismic waves could reach Alaska and even the Russian Arctic. There is also a real domino effect risk, as one powerful quake could trigger activity along other faults across the northern part of the continent. What is this place where the frozen crust began to move? Why had this fault been ignored? And when will it strike, reshaping the geopolitical map? Deep in the Canadian bush lies a giant fault more than 1,000 kilometers long. It had remained silent so long that scientists believed it dormant. The story began only recently when a team from the University of Victoria decided to revisit this forgotten Tentina fault using modern technologies. They found that centuries ago along the fault line, some of the most powerful earthquakes had shaken entire regions. But why had this monster stayed hidden for so long? Most of the fault crosses nearly uninhabited terrain, thick forests, mountain ranges, and Arctic wastes where settlements lie hundreds of kilometers apart. European researchers arrived late, and satellite technology only appeared at the end of the 20th century. Moreover, the Tentina Fault has long remained in the shadow of its more famous neighbor, the Denali Fault in Alaska. In 2002, that region experienced a magnitude 7 to 9 earthquake, the largest intraplate quake in North America in 1.5 centuries. The ground ruptured along a stretch of 340 kilometers in just 1.5 minutes. Maximum surface displacement reached nearly 9 meters. This event drew the attention of seismologists to Alaska, yet the Tentina remained overlooked. And still, satellite imagery from recent years revealed something terrifying. Using high-resolution data, scientists could peer through the dense canopy and glimpse what lay beneath all these years: linear ledges, displaced river channels, and deformed rock formations. All of it pointed to catastrophic events long past, according to lead researcher Taryn Finley. Over the last 20 years here, only faint tremors measuring 3 to 4 on the scale had been recorded. There was no indication the fault could unleash more. Yet satellite technology forced researchers to view the problem from a different angle. What they saw left no room for doubt about the true power of the sleeping giant. To grasp that power, scientists deployed a full arsenal of modern tools. Satellites scanned the surface with extraordinary precision, while lidar on planes and drones pierced the forest canopy to produce detailed three-dimensional maps of the terrain. Each new image deepened the alarming picture. What appeared as ordinary hills as valleys proved to be gigantic scars from ancient cataclysms. These features told a terrifying story. Originally, they formed a single massif, but a sequence of mighty earthquakes tore them apart and scattered the blocks along opposite sides of the fault. Today, a gap about 1 kilometer wide separates them, and that is only the beginning. Researchers traced how quickly tectonic stresses accumulate and found the Tentina Fault itself is growing. To gauge the scale of the stored energy, they compared Tentina with other known faults and with planetary motion, concluding its movement resembles a right lateral shear like the famed San Andreas Fault in California. But there is one crucial difference that makes the Canadian fault far more dangerous. San Andreas releases energy in recurring earthquakes of varying strength, gradually relieving the tension. Over the past 150 years, California has witnessed many strong quakes, including the catastrophic earthquake of 1906 in San Francisco. That pattern is hazardous for residents, yet geologically safer because energy is shed in portions rather than piling up to a single rupture. Tentina behaves very differently, lying dormant for tens of thousands of years and then delivering one monstrous jolt. Geologists classify such structures as low slip rate faults and regard them as among the planet's most dangerous. When the accumulated energy finally releases, the ground can shift by several meters in a matter of seconds. That mechanism was at work in 2011 during the Great East Japan earthquake, when the Pacific Plate had long been subducting beneath the Japanese archipelago, and a rupture of magnitude 9.1 moved the land about 2.5 meters to the east, triggering devastating tsunamis. GPS monitoring shows the ground around Tentina continues to deform even now. Satellites record a slow but steady buildup of stress, indicating the process has not ended and the geologic spring remains pressed toward a critical point. Scientists are especially troubled by 20 years of micro-earthquakes in the Tentina fault zone. The events are minor, barely above magnitude 3, and many go unnoticed by people. Yet for geologists, they signal something unsettling. Such microquakes often precede a major rupture. Leading researchers describe the fault's present state in plain terms, suggesting the Tentina is already nearing the late stage of its seismic cycle. A slip deficit of 6 meters has accumulated, and when it releases, the quake could reach at least 7.5 in magnitude. A 7.5 quake is not merely a number. It would unleash a destructive force capable of turning a region into a disaster within minutes. By comparison, it would dwarf the Northridge earthquake of 1994, which wrecked thousands of buildings in Los Angeles and caused losses of $20 billion. And it would rank among the 5 most destructive natural disasters in North American history. The true nightmare would unfold after the shaking subsides. The Tentina region sits atop a geology that can magnify any large quake into a planetary-scale catastrophe, driven by enormous landslides that could strike thousands of square kilometers at once. The slopes around the town of Dawson rest on unstable blocks of rock, formed over millennia as water infiltrated cracks, froze, expanded, and split the rock. In summer, meltwater undercut the bases, making them even less stable. In an earthquake, 5 landslides could break loose and reach central Dawson in 3 to 4 minutes. Mud flows could race at around 100 kilometers per hour, leaving little time for evacuation. Even if the city avoids the worst of the ground shaking, other trials remain. The fault runs beneath crucial transportation corridors, including the Klondike Highway and the region's only year-round road linking Dawson with the wider world. An earthquake could tear this route into many fragments, isolating the town for weeks or months. The impact on the region's mining industry would be no less severe. Yukon, one of Canada's largest gold-producing areas, hosts dozens of mines and ore processing plants, many perched near the fault or on unstable slopes. An earthquake could ruin expensive equipment and trigger an environmental disaster, including spills of toxic chemicals used to extract gold from ore. Ecologists warn about the enormous tailings ponds that hold mining waste containing cyanides and heavy metals. If those dams failed, the toxic substances stored in their reservoirs could spill into the Yukon River, poisoning the water for hundreds of kilometers downstream. History records many cases where dormant faults woke and unleashed destruction. In 1811 to 1812, a sequence of powerful earthquakes shook the Mississippi River Valley in central United States. The epicenter lay along the New Madrid Fault Zone, long regarded as entirely inactive. The shocks were so intense that they were felt as far away as Cincinnati, about 1,600 kilometers from the epicenter, and the Mississippi briefly reversed its course. Yet the Tentina Fault may be even more dangerous. Its geographic position makes it a potential trigger for a cascade of catastrophic events that could affect not only Canada but neighboring regions as well. Tectonic processes in the Arctic are tightly interlinked, so a tremor somewhere can awaken others thousands of kilometers away. Of particular concern is the connection between the Tentina and the famous Dinalia Fault in Alaska. These two colossal fractures lie roughly parallel and are joined by a network of smaller faults. A powerful quake on one could set off its neighbor, and the 2002 event on Dinalia already demonstrated the potential destructiveness of such a chain. The Dinalia quake triggered thousands of landslides across the Alaska Range. Seismic waves from that quake even reached Texas and Louisiana, provoking dangerous shifts in water levels in wells and reservoirs. Perhaps the most astonishing effects were the awakening of volcanoes and geysers far away, as hydrothermal fields grew more active and some geysers altered their eruption patterns. Now imagine both faults awakening simultaneously, with Dinalia and Tentina active at once. Scientists would call such a scenario cascading destruction, where one quake begets another, perhaps even a third. Such a cascade could sweep across the northwestern part of North America, from British Columbia to the Arctic Ocean. It could disrupt the Arctic transport network, halt oil and gas production, and cripple bases and early warning systems. The Doolin radar system, which monitors Arctic airspace, would be especially vulnerable as a key component of North American defense. International consequences could be severe, with the Arctic turning into an arena of competition among Russia, the United States, Canada, Norway, and Denmark for control of its territories and resources. A disaster of that scale could fundamentally redraw the geopolitical balance in the region. Although the Tentina Fault lies in Canada, seismic energy could reach Russian Arctic basins and industrial facilities on Chukotka. Today, the Tentina Fault remains under constant observation by an international team of scientists. A segment near Dawson attracts particular interest, where traces of ancient earthquakes are best preserved. Here, researchers plan to drill a series of deep boreholes to study crustal structure several kilometers beneath the surface. The gathered data should illuminate the fault's mechanism and the amount of energy it has stored. Canadian authorities are not idle, and the National Seismic Hazard Model is being revised in light of the new Tentina data. For the first time, this fault will appear on the official seismic risk map as a distinct source of potential danger. That change implies that regional building codes may be reviewed, updated, and tightened. Yet these measures could prove useless if an earthquake unfolds with the forecast magnitude of 7.5 or more. In the insurance sector, concerns are growing as well. A new hazard source could fundamentally alter regional risk calculations. Insurance costs, property values, and business exposure around the area could rise markedly, with some properties potentially losing coverage. Satellite data indicate that strain buildup along the fault persists, with slip deficits increasing by a few millimeters each year, edging the fault toward a critical threshold. When that threshold will be reached remains unknown, It could occur tomorrow, or in 10 years, or in 100 years. Geologic time moves by its own rules, beyond ordinary human prediction. Yet one fact is clear. The Tentina fault has decisively altered scientists' view of seismic risk in northern regions, turning what once seemed stable into a potentially deadly reality. If the researchers' forecasts prove correct, humanity may witness one of the most powerful natural catastrophes in modern history.